7.4 Potential difference in electric potential. Recall that in a region of space where the electric field is constant, the electric field has the same magnitude and direction at all points. A point charge Q in this region experiences an electric force as can be described by this equation. Electric force is equal to charge times the magnitude of the electric field. In order to help with your understanding, I want you to compare, whenever you can, this equation to a concept of fields that you're much more familiar with, and that is the field of gravity. This equation is completely analogous to the equation for gravitational fields, mg, where instead of mass, we're looking at charges, and instead of electric field, we're looking at the gravitational field. Okay. The electric force is parallel to the electric field as shown in the diagram below. Suppose this charge moves a certain distance, delta d, starting at a point A and ending at a point B. For simplicity, assume this displacement is parallel to the electric force. According to the definition of work, the work done by an electric force on a charge is F delta d. Electric potential energy. This is the energy stored in a system of two charges a distance delta d apart, or the energy stored in an electric field that can do work on a positively charged particle. And again, I want you to, in the back of your head, to understand this concept, compare it to that of electric fields, rather gravitational fields, because there are so many analogies and it will actually help you understand this section. So we know that the change in energy is equal to the work done. So the change in energy will equal the electric force times the displacement. And we can replace that with this equation here. Charge times the electric field intensity times the displacement. This would be, if we compare it to gravity, would be equivalent to mg delta t. Okay, now let's take a look at diagram A and diagram B. In diagram A, we see the direction of the electric field is moving from left to right. And in this situation, to move a charge from point B to point A, the external force acting on a charged particle works against the electric field. We're moving in the opposite direction of the electric field, and therefore produces a positive change in electric energy. So if you imagine, if you are doing work to move something against an electric field, it will contain stored electric potential energy. And when released, that particle can then accelerate through this electric field. Same thing is true when we lift a mass opposite direction against the field of gravity. That stores gravitational potential energy. In diagram B, the charged particle takes energy stored in the electric field and converts it into kinetic energy. Here, the particle is able to move in the direction of the electric field. This will produce a negative change in electric potential energy because the particle is converting electric potential energy into kinetic energy. Therefore, there will be a loss in electric potential energy, and the change in potential energy is therefore negative. Let's try sample problem number 1. Potential energy difference in an electric field. A charged particle moves from rest in a uniform electric field. Part A. For a proton, calculate the change in electric potential energy when the magnitude of the electric field is 250 newtons per coulomb, the starting position is 2.4 meters from the origin, and the final position is 3.9 meters from the origin. Let's write down what we have. We know the magnitude of the electric field is 250 newtons per coulomb. we know the distance covered by the charge. If it's moving from 2.4 meters from the origin to a final position of 3.9 meters from the origin, we can calculate it as 3.9 minus 2.4, which is 1.5 meters. Since we're dealing with a proton, we know the charge of a proton is plus 1.6 times 10 to the power of negative 19 coulombs. And what they want us to find is the change in electric potential energy. From above, we know that the change in electric potential energy is equal to negative Q epsilon delta D. We can sub these values in. Since we're dealing with a proton, we know that the charge of the proton is positive. It's 1.6 times 10 to the power of negative 19 coulombs. The magnitude of the electric field is 250 newtons per coulomb. And the distance traveled is 1.5 meters. If we punch this into our calculator, we end up with negative 6.0 times 10 to the power of negative 17 joules. Therefore, the change in the electric potential energy due to the movement of the proton in the uniform electric field is negative 6 times 10 to the power of negative 17 joules. The negative sign indicates that the electric field loses potential energy by doing work on the proton, and as a result, the proton gains kinetic energy. Let's do the same question. This time, we're going to find the change in electric potential energy for an electron in the same field with the same displacement. So what remains the same? We have the same magnitude for the electric field. The displacement is still the same, 1.5 meters. Now we're looking at the charge of the electron, which is negative 1.6 times 10 to the power of negative 19 coulombs. And we want to find the change in electric potential energy. We'll use the same equation. Change in electric potential energy is equal to negative Q epsilon delta D. That's negative. Now I'm going to just make sure that we are putting our charge in correctly. Negative 1.6 times 10 to the power of negative 19 coulombs times 250 newtons per coulomb and a displacement of 1.5 meters. If we punch this in, we end up with plus 6.0 times 10 to the power of negative 17 joules. So the change in electric potential energy due to the movement of the electron in the uniform electric field is 6.0 times 10 to the power of negative 17 joules. The positive value indicates that the electric field gains potential energy and can store this potential energy as the electron is forced to accelerate against the field. Okay, in part C, we want to calculate the change in electric potential energy for an electron accelerated in an electric field with the same magnitude but opposite direction as in parts A and B, and with a starting position of 2.4 meters from the origin and a final position of 5.0 meters from the origin. So let's make a note. The sign of the electric field will be negative. Because the electron is accelerated in the opposite direction. Okay. So, for the electric field, we have the same magnitude, but now this time, because we're going in the opposite direction, we're going to change the sign of the electric field, 250 newtons per coulomb. The distance traveled will be 5 meters minus 2.4 meters, which is 2.6 meters. The charge of the electron is negative 1.6 times 10 to the power of negative 19 coulombs, and we want to find the change in electric potential energy. Using the equation from up above, it's equal to negative Q epsilon delta D. That's negative. And we're going to make sure we have our values in the proper sign. 1.6, negative 1.6 times 10 to the power of negative 19 coulombs. Since we're accelerating in the opposite direction, this will be 250 newtons per coulomb times a distance of 2.6 meters. Punch this into your calculator. You will get negative 1.0 times 10 to the power of negative 16 joules. Now this time, since the electron is moving in the opposite direction, it will be losing electric potential energy and therefore gaining kinetic energy. So when the direction of the electric field is reversed, the change in electric potential energy is negative 1.0 times 10 to the power of negative 16 joules. The negative value indicates that the electric field loses potential energy by doing work on the electron. And in this case, it gains kinetic energy. And we'll look at the law of conservation of energy and how a loss in electric potential energy equals a gain in kinetic energy. Much like when you move a mass through a gravitational field, any loss in gravitational potential energy equals a gain in kinetic energy. So the perfect example to start with that uses the law of conservation of energy is sample problem number 2, where we're looking at the dynamics, the movement of charged particles. Part A. Using the law of conservation of energy, calculate the speed of the proton in part A of sample problem number 1 for the given displacement. Assume that the proton starts from rest. Okay, the law of conservation of energy tells us that the change in gravitational potential energy plus the change in kinetic energy equals 0. So we know that the change in gravitational potential energy plus 1/2 mv squared equals 0. We can rearrange this to solve for v. Speed is equal to 2 times change in gravitational potential energy divided by mass. We know the mass of the proton is 1.67 times 10 to the power of negative 27 kilograms. And from up above, in sample problem 1, part A, when we're looking at the proton, we determine that the change in gravitational potential energy was 1.6 times 10 to the power of negative 17 joules. So we can sub these values in. And we can determine the speed, the final speed of the proton is 2.7 times 10 to the power of 5 meters per second. So the speed of the proton accelerated for a distance of 1.5 meters by an electric field of magnitude 250 newtons per coulomb is 2.7 times 10 to the power of 5 meters per second. In part B, we want to determine the initial speed of the electron in part B of sample problem number 1. Assuming that the speed has decreased to half its initial speed after the same displacement delta D. Okay, so let's write down a few things we know. We're dealing with an electron. So the charge of the electron is negative 1.6 times 10 to the power of negative 19 coulombs. We know the magnitude of the magnetic field, or the electric field rather, 250 newtons per coulomb. We know the displacement from part B was 1.5 meters. We know the mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. If the mass of the electron or the mass of the proton are not given in a question, it's your responsibility to find these values. They're easily found in the appendix of any textbook, so make sure that you find them. In fact, it doesn't hurt to write down the mass of the electron, the charge of the electron, or the mass of the proton, the charge of the proton, as soon as one of these particles is mentioned in your question. Okay, a couple of things. We know that the change in electric potential energy plus the change in kinetic energy is 0. We also know that it says the speed has decreased to half its initial speed. So the final speed of the electron will equal 1/2 the initial speed of the electron. Okay? So, using this statement here, the law of conservation of energy, we know that the change in electric potential energy is negative Q epsilon delta D, plus the change in kinetic energy will equal 1/2 mv final squared minus 1/2 mv initial squared. Let's take this guy, bring it over the equal sign. What we're left with is 1/2 mv final squared minus 1/2 mv initial squared equals negative Q epsilon delta D. Now, I told you that the final velocity is equal to 1/2 the initial. So I'm going to place that in here. So I have 1/2 m, and instead of VF, I'm going to write 1/2 VI squared minus 1/2 mvi squared equals negative Q epsilon delta D. Now let's square what's inside this bracket. We end up with 1/2 m 1/4 vi squared minus 1/2 m vi squared equals negative Q epsilon delta D. We can simplify this. 1/2 m times 1/4 is equal to 1/8 mvi squared minus 1/2 mvi squared equals negative Q epsilon delta D. If we have 1/8 mvi squared minus 1/2 mvi squared, 1/8 minus 1/2 is equal to, hopefully your knowledge of fractions is up to date, that'll be equal to 1/8 minus 1/2. That's like 1/8 minus 4/2 is negative 3/8 mvi squared equals negative Q epsilon delta D. Forgot, when we brought this over the equal sign, these should be positive, so make sure that you're making these positive. Okay? All right, let's solve for VI. It's equal to the square root of 8 times Q epsilon delta D divided by negative 3m. We can sub and solve. That's 8 times negative 1.6 times 10 to the power of negative 19 coulombs times 250 newtons per coulomb times 1.5 meters divided by negative 3 times the mass of the electron, 9.11 times 10 to the power of negative 31 kilograms. Hopefully what's under the square root becomes positive, and in fact it does. If you sub this into your calculator, hit enter, you should get 1.3 times 10 to the power of 7 meters per second. Great. Now let's take a look at the concept of electric potential. You studied this briefly in grade 9 and again in grade 11. Electric potential is the value in volts of the potential energy per unit of positive charge for a given point in an electric field. So the symbol for electric potential is V, and it's equal to the amount of electric potential energy per unit charge. So V is equal to E over Q. Now, electric potential difference is the amount of work required per unit charge to move a positive charge from one point to another in the presence of an electric field. In the case of a uniform electric field, the electric potential difference becomes delta V is equal to delta E over Q. Now, in a uniform electric field, we know the change in electric potential is equal to the work done. And we know the work done is equal to the force times displacement over Q. And we know that the force done is equal to Q times the magnitude of the electric field times delta D over Q. So we can rearrange this and say that electric potential difference, the Q on top and the Q on the bottom will cancel out, is equal to negative epsilon delta D. And make sure that negative sign is there. I believe it's in your notes. I omitted it in mine. We can rearrange this where epsilon is equal to negative delta V over delta D. Okay. Let's try a question. Gets us to practice. We'll look at TV tubes and particle accelerators. The cathode ray tubes in old television sets and computer monitors work in a way that is similar to certain parts in particle accelerators. Both devices accelerate particles in a similar way, using the uniform electric field between two conducting plates. Looked at in another way, the particles accelerate as they move through an electric potential difference. Part A. An electron leaves the negative plate of a cathode ray tube and travels toward the positive plate. The electric potential difference between the plate is 1.5 times 10 to the power of 4 volts. Using the law of conservation of energy and the definition of electric potential difference, calculate the speed of the electron as it reaches the positive plate in a cathode ray tube. Assume that the electron is initially at rest. The mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. So let's write down what we know. Since we're dealing with an electron, we know the charge on the electron is negative 1.6 times 10 to the power of negative 19 coulombs. The mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. We know that the potential difference is 1.5 times 10 to the power of 4 volts. And we want to calculate the final speed of the electron. So we're going to use the law of conservation of energy, which states that the change in potential difference plus the change in kinetic energy is equal to 0. Since the electron is initially at rest, we know that the change in kinetic energy is going to equal 1/2 mv final squared. And we can write in our equation for change in gravitational potential energy, which is Q times delta V. Okay, so we want to solve for V final, which equals the square root of. If we bring this guy over, it will become negative. So it's 2 times negative Q delta V divided by, oh, I forgot to put the mass in there, 1/2 mv final squared, divided by the mass. Let me write that again for you guys. In fact, maybe I'll do it without skipping a step. So we're going to bring this Q delta V over. So we have 1/2 mv final squared equals negative Q delta V. V final equals square root of negative 2Q delta V over M. We're going to sub and solve. That's negative 2 times negative 1.6 times 10 to the power of negative 19 coulombs times a change in potential of 1.5 times 10 to the power of 4 volts divided by the mass, which is 9.11 times 10 to the power of negative 31 kilograms. If you punch this in, you get 7.3 times 10 to the power of 7 meters per second. Therefore, the speed of the electron as it reaches the plate is 7.3 times 10 to the power of 7 meters per second. In part B, we want to calculate the magnitude of the electric field at a distance of 15 centimeters, which is at the end of the cathode ray tube. So we know that the magnitude of the electric field is equal to negative delta V over delta D. So that is negative 1.5 times 10 to the power of 4 volts over a distance of 0.15 meters. Let's punch this into our calculator. We end up with negative 1.0 times 10 to the power of 5 volts per meter. Perfect. Therefore, the electric field has a magnitude of 1.0 times 10 to the power of 5 of negative 1.0 times 10 to the power of 5 volts per meter. The negative sign indicates that the field exerts, or extends rather, from high to low potential. The electric field vector always points from regions of high potential to low potential because the electric field is parallel to the direction that a positive charge would move if it were placed at that location. All right. Let's take a look at our last example. An electron moves horizontally with a speed, initial speed of 1.6 times 10 to the power of 6 meters per second between two horizontal parallel plates. The plates have a length of 12.5 centimeters. So this distance is 12.5 centimeters. And a plate separation that allows a charged particle to escape even after being deflected. The magnitude of the electric field within the plates is 150 newtons per coulomb. Calculate the final velocity of the electron as it leaves the plate. So if you imagine, this electron will want to travel in this direction. It's got a velocity, a horizontal velocity that should have it travel parallel to the direction of the plates. But since there is an electric field, and the electric field shows that it's moving from plus to negative in this direction, that's the direction in which a positive charge would travel. If you imagine a positive charge would move from the positive plate to the negative plate. Well, for an electron, this would be the opposite. So as this electron is traveling from left to right, it will be attracted to the positively charged plate. So it's going to cause this electron to have a vertical component to its velocity, which will deflect it up. Let's start by writing down what we know. We know the initial velocity is 1.6 times 10 to the power of 6 meters per second. We know the electric field is negative 150 newtons per coulomb. And the negative sign implies that it is moving opposite to the direction that a positive charge would move because we're dealing with an electron. We know the length, L, is 12.5 centimeters or 0.125 meters. Now, we need to find the final velocity, and the final velocity is going to happen at this angle here. Theta, we know it's going to be composed of the final x component and the final y component. So the final velocity can be found through Pythagorean theorem, which states that the final x component squared plus the final y component squared Okay, now the horizontal component of the velocity will remain the same because what happens horizontally is independent for what happens vertically. This particle is going to travel horizontally with no acceleration in the horizontal direction, but it will accelerate in the y direction. So we know that the final x component, v final x, will equal the initial x velocity, or the initial total velocity in this case, because there was no y component, 1.6 times 10 to the power of 6 meters per second. So in order to find the final velocity, we need to find the final y component as it accelerates towards the positive plate. And we're going to do some creative things mathematically in order to do so. Then we also need to find theta. And theta will be easy. Theta will be equal to the inverse tan of the final y component over the final x component. Okay. So let's start. Let's look at v final y. We know that v final y will be equal to v initial y plus ay delta t. Now, since there is no y component to the initial velocity, this term cancels out and we know that V final Y is equal to AY delta T. So if we want to find V final Y to put in Pythagorean theorem, we need both AY and delta T. Let's start with the acceleration in the Y direction. The acceleration in the Y direction is equal to the net force in the Y direction divided by the mass. The net force in the Y direction is equal to the force of the electric field, which is equal to Q times epsilon divided by mass. So we know the charge of the electron is negative 1.6 times negative 10 to the power of negative 19 coulombs. We know the electric field has a magnitude of negative 150 newtons per coulomb because we're dealing with an electron. And the mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. We can find the acceleration in the y direction by simplifying, and we end up with 2.6 times 10 to the power of 13 meters per second squared. So we can use this to find the final y velocity, which is AY times delta t. The only problem is we don't know what delta t is. We don't know how long this electron will spend traveling through or across that 12.5 centimeters. So how long will it take the electron, whose horizontal speed we know is 1.6 times 10 to the power of 6 meters per second, to travel 12.5 centimeters? Well, speed is equal to distance over time. We know the initial speed. We know the distance is L. Now we got to find time. So time is equal to L divided by initial speed. So that's 0.125 meters divided by an initial speed of 1.6 times 10 to the power of 6 meters per second. So the time it takes to travel is 7.8 times 10 to the power of negative 8 seconds. We can put that value in here to find the final y component. We know the acceleration is 2.6 times 10 to the power of 13 meters per second squared. And we know how long it will be accelerating for. That's 7.8 times 10 to the power of negative 8 seconds. So V final y is 2.1 times 10 to the power of 6 meters per second. So let's find the total final velocity, which is equal to the square root of the final x component squared plus the final y component squared. Put that as a superscript. Okay, so the final velocity is equal to the square root of, we know the final x component is equal to the initial x component, which is 1.6 times 10 to the power of 6 meters per second. We're going to square that, plus 2.1 times 10 to the power of 6 meters per second. We're going to square this, take the square root of both. We know the magnitude of the final velocity is 2.6 times 10 to the power of 6 meters per second. Perfect. Now let's find the angle of this final velocity, which is equal to the inverse tan of V final y over V final x, which is 2.1 times 10 to the power of 6 over 1.6 times 10 to the power of 6. Theta equals 52 degrees. So the x component was this direction, the y component was this direction. Theta would be this angle, which is 52 degrees north of east. So we can state that the final velocity of the electron is 2.6 times 10 to the power of 6 meters per second, 52 degrees north of east. Okay, that may not seem straightforward. There might not be a chance that you would have gotten this on your own, but having shown you how to do it, and if you commit to practicing how to solve questions like this and retrying this question on your own as many times as it takes for you to be comfortable, is exactly what you need to do to be proficient in this section. I've assigned practice problems on page 349 and 353, as well as review questions on page 354. Now, good luck.